The topic of this technical webinar is soil drying for high voltage cable ampacity calculations. This is a live technical event. Some webinar housekeeping. Please leave your camera on or turn it on for more lively interaction during the event. There's nothing worse than me speaking to just a computer screen. I'd love to see your faces. Microphones will be muted during the webinar. Please keep them muted. Send your questions in the chat throughout. At the very end, there will be a live Q&A where I will attempt to answer your technical questions. Please stay until the end to receive your certificate of attendance. There will be a form link that's given at the end of this webinar. You will need to fill it out and we will email you a certificate. This is one of a series of live technical webinars. Go to luma/elec. You will see some of the scheduled events that are upcoming, but we have over 20 that are scheduled for this year, free technical webinars. In this presentation, I will quickly introduce Elec Cable HV software. I will talk about the fundamentals of soil drying calculations, including the IEC standards, CGRE documents. I'll talk about thermal resistivity of soil, the fundamentals of soil drying, soil dryout prevention, the calculation models for considering soil drying, the multi-zone model, and then I will present some calculation examples, including a live software demo, 2 examples in total. Those should be really quite interesting for everyone. I will end the webinar with some conclusions, recommendations, and we'll have a Q&A session at the end. So briefly, what is Elec Cable HV software? That software has been used for the modeling in this webinar. It's accurate and validated software for cable rating calculations from low voltage to high voltage, including HVDC. Fully complies with IEC 60287 standards. You can perform current rating calculations for custom cables under your specific installation conditions, which is very, very important. You can see along the top, it applies to a very wide range of installation conditions, includes the finite element technique. And if you would like to download a free trial, fully functioning, by the way, you can visit elec.com and go to the Elec Cable HV software product page and just request a free trial to download. Just let me let in a couple more people. IEC 60287 current rating calculations. This is the penultimate series of standards that provides analytical equations for cable current rating calculations. These standards continue to be widely adopted because they are applied to common cable types and installation methods. They are reasonably accurate, which leads to reliable, dependable, predictable current rating calculations for new and existing installations, ensuring consistency and comparability between different stakeholders. There are 9 parts to this series of standards. The calculations and the standards are really quite complex. They're very, very detailed, quite ambiguous in some parts, and I'll talk about the CGRE document that clarifies some of that. CGRE Technical Brochure 880 was released in 2022. That's because essentially Many people were doing calculations to IEC 60287 and getting different current rating calculation results. So the working group decided to come together to produce this technical brochure, which clarifies and provides a lot of detailed examples. And we have used that technical brochure to validate our software, and we have complete matching results to the highest precision, which is 11 decimal places if you so wish. But we are matching, we can model all of the case studies and we have exact matching results. Very important and very difficult to achieve. So soil thermal resistivity. For buried cables, the most important parameters are soil thermal resistivity of the native soil and the backfill if applicable, and soil temperature, which is closely linked to earth surface temperature. Actually, soil contributes the largest single thermal resistance and thermal capacitance to buried cables. Thermal resistance or resistivity, I should say, depends on soil type, moisture content, and density, soil density. Controlled backfills often significantly increase ampacity. So in the top right-hand corner, you'll see a table from the IEC, one part of the IEC 60287 standard, which provides some rough approximate thermal resistivity values that you can use. We have a lot more on our website under our technical articles section. And then the photograph is of a site measurement where somebody is performing thermal resistivity tests inside a trench to be used for the cable system designs. From this plot, you can see that cable ampacity is highly sensitive to soil thermal resistivity, whether it's in a backfill or not. The backfill will protect or increase the current rating, but both direct buried cables and cables in backfill are highly sensitive to soil thermal resistivity. That's why it's important to have a good, reliable idea about this value. Soil drying around cables. So the heat from cables may cause significant moisture migration away from the cables. The main cause is the temperature gradient in the soil caused by that heat. A dry soil zone may develop around the cables. There is a sharp transition in thermal resistivity from low value to a high value as drying occurs. Moisture migration, as I've described, is a dynamic process that's extremely complicated. On the right-hand side, you can see this is a soil temperature plot for some cable ampacity calculations. The heating is centralized around the cables and caused by the current flowing in the cables. What are some negative impacts of soil drying? Well, some background. The external thermal resistance significantly influences cable ampacity, accounting for 70% of the temperature increase in buried cables. So the external thermal environment, be that made up of the soil for buried cables, has a very large influence on the current rating. Soil thermal resistivity then obviously significantly affects the external thermal resistance, which in turn greatly affects the current ampacity or the cable ampacity. The outer cable surface is typically 50% to 70% of the conductor temperature. So cable conductors typically operate at around 90 degrees Celsius. And so you can expect that the cable surface temperature would be quite high as well and quite close to that temperature, 50 to 70% of that, which may result in soil drying. If a dried out zone forms around the cables, an abrupt rise in cable temperature may cause thermal runaway, leading to cable damage. There are more or less two famous cases of thermal runaway caused by soil thermal resistivity and dryout. These are a more recent case in Auckland, where there was a power supply failure in 1998, and in London in 1962. The statement from the reports in the bottom right-hand corner in quotes states that it is now suspected that the soil thermal resistivities are higher than the figures used to calculate the ratings for these cables, and that the cables may therefore have been overloaded. So it's a serious concern that has potentially large ramifications in the field. How do we prevent soil drying? We can't really prevent it, but we can do some things to potentially minimize it. We could use a controlled backfill material, which is thermally stable and has a good dry thermal resistivity. We could potentially increase the installation depth of the cables to reach more thermally stable soils, and also lower ambient temperatures of the soil as you go deeper. We could use flat spaced arrangements, cable arrangements, to avoid the concentration of the heat within the soil, thus avoiding or limiting soil dryout. We could also install distributed temperature sensors to detect hotspots before any irreversible damage to the cable insulation occurs. Here's a special case, an interesting case that's happening in the field now, which is related to wind farm landfall. So where the power cables transition from land to the sea, there is a thermal bottleneck which can be greatly affected by soil dryout potentially. In the circled zone above the water table, this is where soil drying is of concern. So the soil can dry out in this area. It's also quite deep. The cables are installed quite deep there. So the deepness and the potential for dryout can cause hotspots, and these can be quite often the thermal limitation for a wind farm. So we should definitely calculate the current rating at the deepest points, just above the water table. There are several models, calculation models that are used for considering soil drying. The most common and popular and covered by the IEC standard is the two-zone method. There is a two-zone method for steady state and a two-zone method for the transient calculations. They are quite different. Mostly we'll be considering the steady state calculations during this presentation. The advantages or the pros of this two-zone method are that detailed soil information is not really required, very detailed. It does, however, require, or we would recommend thermal resistivity measurements of the native soil at ambient and fully wet moisture content, as well as fully dry conditions. So it does require some data. The cons are that it is a relatively simplistic approach to a really quite complex situation. And it does not consider the initial soil moisture content, which can have a significant effect. That's been proven by using a dynamic moisture migration model. So the alternative to these two-zone methods, I should say that the two-zone method is considered really accurate enough, and it is used very widely in the field. to this day. The alternative is to use finite element analysis with dynamic moisture migration model, and to use modified Philip and de Vries equations. This method can deal with steady state and time varying currents. It is really quite complicated. I dare I say that different engineers would implement it differently, so may not be consistent. And it requires very detailed soil information, including laboratory measurements and analysis to arrive at a current rating. Let's talk about the two-zone soil model for soil drying. So the native soil is assumed to be at moist conditions, not fully dry, and it's assumed to have a uniform thermal resistivity. That's a rho S moist soil in the top right-hand corner of the image. Heat dissipated from the cable causes its surface temperature to rise above a critical limit. The surrounding soil will dry out, creating a zone having a uniform thermal resistivity, which is higher than the original or the moist soil. So the dry soil will have a higher thermal resistivity. The dry soil boundary forms an isotherm. So the IEC 60287 equations for calculating current capacity are given here. These are the basic fundamental equations. These have been modified. The second equation is a modification of the first, where these factors V and delta theta X have been added to the calculations. They modify the T4 external thermal resistance calculations. And they allow you to use the two-zone method within the calculations to include soil drying for your current capacity calculations. So the inputs to those calculations are rho D, which is the thermal resistivity of the dry soil thermal resistivity, rho S, which is the thermal resistivity of the moist soil or the native soil. And then we need a critical temperature. What's the critical temperature where soil drying will start to happen or will occur? Where you get that switch or that changeover from a low moist soil thermal resistivity to a dry value. We basically need those three values. Critical soil temperature, this is an important variable. So it's defined as where thermal resistivity starts to change significantly due to moisture loss. It is actually highly dependent on the initial volumetric moisture content of the soil, but that is more or less ignored with the two-zone method. A very common value that is used in the industry is 50 degrees Celsius. However, that is not explicitly stated in IEC 60287. The German standard VDE 0276-1000 does provide a very simple equation for you to calculate this critical soil temperature. It's good because it includes load factor. So you can consider cyclic loading within your critical temperature calculation. We include this in our software because it's quite useful. Also, the document Electra 145 provides critical temperature rise for some soil types. You can see sandy clay, sandy soil, crushed rock, and some selected sands. There are some values given in the table, selected values for different saturation or soil moisture content. That's useful as a reference. There is a relatively simple equation for calculating the critical soil temperature rise, and that's given by Electra 145. The problem is that you will require this down the bottom of the screen. You'll see this plot of thermal resistivity versus soil moisture content. You will need to actually measure this within a lab. So you'll need to take a soil sample from site, and you'll need this plot. And from this plot, we can obtain the critical degree of saturation of the soil, SCR there, and the parameter N we can take from the previous table from lecture 145. You can see on the screen parameter N. That allows us to have a more accurate calculation of the critical soil temperature rise. But it does require some tests. There's a few slides here about the IEC method derivations where you're going from the two-zone method, and we are developing the equations or modification to the IEC 60287 calculation for current. I'm not going to go through this in detail. There are multiple relatively simple steps. So we arrive at this modified IEC 60287 standard calculation for currents. That includes soil drying, considering of soil dryouts. But there are some significant limitations with the IEC implementation of the two-zone method or the two-zone model. The limitations include that it can only be applied to a single isolated cable or circuit. So one cable or circuit. It can only be applied to cables operating at unity load factor or carrying full load current. So not cyclic loads, not cyclic currents. It only applies to direct buried, no backfill installations at standard burial depths, nothing too deep. If you have any questions, please enter them in the chat now. I will answer those at the end of the presentation. So you can see on the left-hand side, this is an example of where the IEC soil dryout method is okay. Single buried circuit buried at standard burial depth, no backfill. On the right-hand side, what if you wanted to consider soil drying to the situation on the bottom right-hand side? We have developed a solution to this. It's really quite complicated, but also very, very useful. Complicated in its implementation, I should say, in the back end. So we developed a multi-zone model named the ELECT method, which extends beyond the IEC limitations, which allows the consideration of soil drying out, cyclic load, backfill and duct enclosures, and multiple circuits with unbalanced loads. They can be carrying different load currents simultaneously. There are almost no limitations. This is actually a world first development. We spend a significant amount of R&D on this, and it's a very, very useful feature to have in your real world for your real world applications. We've also added something else, which is there are some other limitations with the IEC method that considers backfill. It assumes that the cables are located in the center of the backfill and they are all carrying the same load current or having the same losses. In reality, this is not the case. It's a limitation. ELEC software allows you to consider considers the actual cable positions within the backfill, and that they can be anywhere, and considers the actual power losses of the individual cables. This is much more accurate. This can result in differences of around 10% in the current rating. when you do these calculations properly without the IEC limitations. Now I'm going to undertake some calculation examples. I'm going to explain with a couple of slides, and then I'm going to show you in some software demonstrations. This is an example of multiple buried circuits where we are going to consider soil dryout using the elect method. We've got four circuits. On the left-hand side, these four circuits are in trefoil and they are direct buried. You've got some parameters there, the native soil resistivity, the backfill thermal resistivity, and the dry soil thermal resistivity, and the critical temperature, soil temperature, where dryout occurs. Load factor was varied, and I'll show you the results of that. So on the left-hand side, we've got current ratings for direct buried, and on the right-hand side, we've got current ratings for in backfill. You notice that the current ratings in backfill are slightly higher than the direct buried. For example, the lowest current rating, so the middle cable, circuit number 2, the current rating for direct buried is 425 amps. And for in backfill, the circuit 2 has a current rating of 455 amps. For obvious reasons, for the backfill has a lower thermal resistivity. So in these plots, on the left-hand side, we've got the two examples, one in backfill, one without backfill. We've got soil temperature plots. We fixed the load current, so the cables are all carrying the same load current, 486 amperes, and we turn soil drying on and off. So on the left-hand side, you've got without soil drying, and on the right-hand side, when we are considering soil drying. So what you see is, if you consider soil drying out, the cable temperatures, the soil temperatures dramatically increase. And this can lead to the thermal runaway of the cable. So you must reduce the current capacity of the cable if you're going to experience or consider soil dryouts. This plot shows the variation of the current capacity of the hottest cable. That's circuit 2 of those four circuits for the direct buried case and the in backfill case, both with and without soil drying. You'll notice that the slope of the curves show that the top two curves are for in backfill. The current rating is higher. And you'll notice that due to the slope of the second curve from the top, you'll notice that backfill almost protects cables from soil drying out and makes the current rating less sensitive to soil drying. I'm going to quickly demonstrate this example in the software just briefly. Let me share my screen again. Okay, so hopefully you can see the software. Let me show you the cable model. This is a 240 square mil medium voltage cable. Move that out of the way. Let's look at the general settings. So it's an extruded single core 33 kV cable operating at 50 hertz. The cable model was built in the metric system, but could also be built in the imperial system of units. It has a 240 square mil conductor. On the left-hand side, you'll see the cable layers that we have in this cable. So we've taken a cable data sheet and we've replicated in the software. So what we do is we add or check the layers that we have in the cable according to the cable data sheet. And then we go through each of those layers and we enter the properties. So for example, the insulation, the diameter, the thickness, the maximum operating temperature, the insulation type. You can have custom types, electrical capacitance. There's a huge database behind this. There is also a database of pre-modeled cables, so you don't actually have to do it like this. Importantly, these cables, complex cables, often need to include custom layers, usually custom insulating layers. So we can add those in the software and define those according to many different types of insulating materials. So once we've modeled the cable, and like I said, there's already a database of pre-modeled cables. We would also set the bonding arrangement, but I'll show you the installation settings. So in this case, I've set the cable circuits to operate at a maximum conductor temperature of 90 degrees, which matches the insulation temperature, but I can also customize that. And in this case, I'm using a load factor of 0.9. And we can change the bonding arrangement from solid, single point, or cross bonding. And then so I'll close the cable systems navigator. Our calculations are performed live. So you can see this is the direct buried installation method. We've got four circuits buried at 0.75. I can the software is fully interactive, so I can move the circuits around. The current rating will be updated live. These are fully iterative calculations. And then on the right-hand side of the screen, I need to move something out of the way. You will see the results displayed here, and we can click between the different results of the losses, thermal resistances, cable temperatures, etc. There is a soil temperature plot, which is also updated live. And along the bottom, actually our software works a little bit like Excel. So you can have different tabs. So you can set up different installation scenarios, because along a cable route, the installation will vary. So you'll take cross sections along the route, and this allows you to model different sections within the same project. So here you'll see section 2, it has a backfill. And the backfill is defined here. It has a custom thermal resistivity, has some custom properties. I can also adjust the backfill on the screen, but I could enter exact dimensions into the controls here. And there is a soil temperature plot which displays the backfill. You'll see the hottest point on the backfill caused by the cables in there. And soil dry out. So this is where we consider soil dry out. So we can turn soil dry out on or off. So this is with soil dry out off. As I mentioned, the calculations are fully iterative. There's a lot of calculations happening behind the scenes. So without soil dry out, you can see the current rating for these circuits. We're on the unequally loaded setting. And so 520, 490 for the middle circuits. These are more affected by the mutual heating, so the middle circuits have a lower current rating. Let's turn soil dry out on. And these current ratings should drop. So 520. So now we've got 485, 450, 450. So there's a significant difference when you consider soil dry out. And these are our soil dry out settings. We've got a dry thermal resistivity of 2.5, and this is the critical temperature. If we reduce the temperature, our current rating would go down again. So if we reduce that to 40, these currents will go down again. Just let the iterations happen. a few more iterations because we've reduced the soil drying temperature limit or, or criteria. So that's our first example. Now I'm going to move on to our second example. So let me just stop sharing my screen and then reshare the presentation. This is going to be a really practical industry example. So there's just one slide that I want to go through. So this is a typical industry example where a utility, this is a utility standard, Ausgrid in Australia, which is quite a famous utility here. Let me go through their requirements. So Ausgrid, I'll just read this paragraph. Ausgrid assumes dry out will begin when the native soil is exposed to a temperature of 50 degrees Celsius. That's that limit that we've been talking about, the critical temperature. It is acknowledged that this is a moderate position, and some locations within sandy soils dry out at a temperature limit lower than this, yes. So we may need a lower limit for sandy soils, say 40 degrees. Thermal stability shown via the 50-degree isotherm modeling should be included in the ratings report unless it's determined it's not required. One way to manage the risk of dryout is to ensure the 50-degree isotherm is fully within the thermal stable backfill material. So what we see here is a cross-section of a trench. In the middle, the grey area, we've got 3 cables installed in a thermally stable backfill. So what they're assuming, what is usually assumed, is the backfill is not susceptible to dry out. Well, it is, but it has a known a dry thermal back resistivity, which is quite good. And so we are not worried about dry out within the backfill. So what we can do is we can adjust or reduce or limit the current carried by the cables so that the 50-degree isotherm is contained within the backfill, thus avoiding soil dryout of the native soil, because we are relying on the thermal resistivity of the native soil or the moist soil, and we don't want to dry it out. So I'll show you how you can achieve that using software. I'll just quickly stop sharing the presentation. I'll share the software screen again. Let me open the relevant project. That's not the right one. Sorry about that. So in this case, we've got a single circuit in flat arrangement installed in ducts inside a backfill. Looks like we're using custom arrangements, so custom cable positions, but you can use standard positions. And the ducts are defined here. Different duct materials are available. You can also fill the ducts with air or water or solid fill. And they are flat and spaced within the backfill. The backfill is defined here. And in this example, this first case, we've got soil dry out turned off. So we are not considering soil dry out. And in this example, this first example, the bonding arrangement is solidly bonded. So the screen or the sheath is solidly bonded. Let's have a look at the results. So the current capacity of the circuit is 630 amps. It's a 132 kV cable. I'm just looking at the results on the right-hand side. Let's look at the losses. We've got a sheath, because the cable sheath is solidly bonded, we've got a sheath circulating current of 274 amps. All of the electrical properties are defined here. Thermal resistances, cable temperatures. So the conductor temperature is limited to 90 degrees. That gives us the current rating of 630 amps. And you can see that the duct outer temperature is, as a result of conductor temperature, is 64 degrees. That's the temperature of the outer duct. That temperature is going to potentially cause the soil drying. So this first case is for solidly bonded. Now I'll look at the bottom, you'll see the tabs that I have. I can look at the single point bonded case. So it's this, I've switched to that now. It's the same installation conditions, only that the sheath is single point bonded. So let's look at the losses. I don't have a sheath circulating current. I have a sheath standing voltage because the sheath is single point bonded. Let's look at the cable temperatures. The conductor temperature is obviously 90 degrees. Looks like the duct outer temperature is slightly lower, and yet the cable rating is significantly higher because we don't have those sheath circulating currents. So let's move on to the same case with soil dryouts. So basically, it's this solidly bonded case when I consider soil dryout. So before soil dryout, I've got a current rating of 630 amps. When I turn soil drying on, the current rating goes down to 555 amps. So let's look at the settings. I'll just turn that off for now. We've got consider soil drying around the cables. And so it's 600 amps versus 630. So the backfill is providing some protection, but still with soil dryout considered, we need to reduce our current rating to not exceed the temperature limit of the cable. So these are the settings for soil dryout. 2.5 is the dry soil thermal resistivity. The critical temperature was 50 degrees. Let's look at the soil temperatures. So I'm going to show you another interesting setting, which is soil dryout prevention. You can see that the temperatures in the soil are within the backfill exceed 55 degrees, and actually just outside of the backfill, we have a temperature of exceeding 50 degrees. 55 degrees isotherm is there, the red, and the orange is 50 degrees. So in that area below the backfill, we are going to see the soil is going to dry out, and the thermal resistivity of the soil is going to significantly jump. So what we can do is, in line with the Ausgrid criteria, they want us to avoid soil drying out in the native soil. So we need to confine the 50-degree isotherm to be within the backfill. So to do that, we simply turn on prevent soil drying outside of backfill. There are some other settings that we have to limit cable temperatures. We can limit the cable jacket temperature, but this is a really handy feature. Just turn that on. Prevent soil drying outside of backfill. And you will see now that the 50-degree isotherm or temperature is confined within the backfill. So no native soil is going to dry out. Now, the drawback of this is that we have a further reduced current rating. So without considering soil dry out, we've got 630 amps. When we just had considering soil dry out without preventing soil dry out or confining soil dry out to the backfill, we had 600 amps. When we prevent the temperatures exceeding 50 degrees to go outside of the backfill, we further reduce the current carrying capacity, but we meet the criteria. Soil drying out will no longer, or the chances of soil dry out will be greatly reduced and will meet the criteria of the utility in the design.